This presentation continues our work on binomial series. Grade E students will be able to expand a plus bx all to the power of n. Grade C students will be able to find a range of values upon which the binomial series is valid. Grade A students will be able to use partial fractions to find a binomial series of algebraic fractions. Section 7. Binomial series a plus bx to the power of n on page 17 of the C4 notes. Now, since the formula for rational powers of n requires the function in the bracket to be 1 plus rather than any other constant plus, we need to rearrange to be able to use the formula. So what we do is we factorise the a out. So we get a outside, 1 plus b divided by a, x, and then all to the power of n. So what we have to raise both parts to the power of n, so it's a to the power of n times 1 plus b over a x to the power of n. And then basically we use the same formula that we did before to expand 1 plus b over a x to the power of n. Now basically in the exam, 99 times out of 100 we will have to deal with functions of this kind rather than just dealing straight with the 1 plus type. So in this example we're expanding in ascending powers of x up to and including x cubed. We start with 4 minus x all to the power of minus a half. So what we do is we need to take 4 out. We'll need to raise that to the power of minus a half. And then inside the bracket we'd get 1 minus x over 4 to the power of minus a half. Now 4 to the power of minus a half is equal to a half. So when we do after we've done our expansion, we'll have to multiply each term by a half. So to remember, we should do our expansion within a bracket with a half on the outside. So same formula as before, it's 1 plus nx. N for this one is minus a half. X, as I like to put in inverted commas, because of the abuse of notation, is equal to minus x over 4. So 1 plus nx gives us 1 plus minus a half times minus x over 4. Plus n times n minus 1 so 1 less than minus half is minus 3 over 2 all over 2 factorial minus x over 4 all squared, and then for the cubed term minus half times minus 3 over 2 times 1 less, which is minus 5 over 2, all over 3 factorial, minus x over 4 cubed, plus dot dot dot, close our bracket. Now we'll need to calculate each of these terms. Before timesing by the half at the front. So it's still 1 plus, and actually check, minus a half times minus x over 4 will give us plus an 8th x. With the next term we've got minus a half times minus 3 over 2 Divide by 2 factorial. Which gives us 3/8 of the coefficient outside the bracket of minus x over 4 squared. Now remember, when we square that bracket, we'll not only just get x squared, but we'll get minus a quarter squared. So we'll need to times the 3/8 by minus a quarter squared. And we get 3 over 128 using my calculator. Then on to the next one. So we've got minus half times minus 3 over 2 times minus 5 over 2 over 3 factorial gives me minus 5 over 16. Again, the minus x over 4 is all cubed, so we would also have to times by minus a quarter cubed for our coefficients. We get 5 over plus 5 over 1024 x cubed. Then we times each of those terms by a half, so a half times 1 is a half. Half times an 8th x is a 16th x. Half times 3 over 128 is 3 over 256. And a half times 5 over 1024 is 5 over 2048 x cubed. We'll start that. We also need to state the values for which the expression is valid. The expression is valid for the expansion of 1 plus x to the n when the modulus of x, and I'm going to use the inverted commas again, is less than 1. X is minus x over 4. We shouldn't go back to the original function, the 4 minus x to the minus a half. We should be using the one that we're expanding, the 1 minus x over 4 to the minus a half. Now we can ignore minuses because of the modulus signs. So the modulus of x over 4 is less than 1. So this expression is valid when the modulus of x is less than 4. So same sort of idea for example part B. Example 1 part B, we've got 2 minus 4x to the 3 over 2, so we'll have to take the 2 out. So remember that 2 is also raised to that power of 3 over 2. And when we take the 2 out, we'll get 1 minus 2x, and again that will be raised to the power of 3 over 2. Now if we stick 2 to the 3 over 2 into our calculator, we get a horrible decimal. It's 2.828427125. Now we can break it down into 2 to the power 1 times 2 to the power half, which is 2 root 2. Now in practice we haven't seen anything involving surds in these sort of questions in an exam, but it is theoretically possible. So this example just shows how we would deal with it. So again, we leave our 2 root 2 on the front, and then we use our usual binomial expansion formula. So 1 plus nx, in this case our n is the 3 over 2, and our x is the minus 2x. And then n times n minus 1, so 3 over 2 times 1 less, which is a half, over 2 factorial minus 2x all squared. And then because we're going up to x cubed, what we've got so far, the 3 over 2 times a half times 1 less again, which is minus a half, all over 3 factorial times minus 2x all cubed. So multiplying out, you get 1, 3 over 2 times minus 2x will give us minus 3x. Then 3 over 2 times a half, all over 2 factorial, times the minus 2 squared will give us 3 over 2. And x squared. And then 3 over 2 times a half times minus a half all over 3 factorial times minus 2x all cubed. So the 3 over 2 times a half times minus half all over 3 factorial times minus 2 cubed for the coefficient part. And we'll have x cubed at the end. We're going to get plus. And again, use calculator for this to make sure you're getting it right. A half x cubed. Start that. Multiplying out. You get 2 root 2 minus 6 root 2x. Plus 3 root 2 x squared plus root 2 x cubed. Let's start that. We also need to know where it's valid. Again, we shouldn't be using the original function, we should be using the bracket with the 1 plus or minus. So we're going for the modulus of 2x is less than 1. So modulus of x has to be less than a half for this binomial series to be valid. Now, when we did partial fractions, one of the things we said that we could use it for is for expanding binomial series for algebraic fractions. So in this case we need to start off by expressing f of x in partial fractions. Now partial fractions, x over 3 minus 2x times 2 minus x is a over 3 minus 2x plus b over 2 minus x. Now if we multiply through by the denominator, we get x is equal to a times 3 minus 2x times 2 minus x all over 3 minus 2x. 3 minus 2x's cancel and we get a times 2 minus x. The b over 2 minus x times 3 minus 2x, 2 minus x. The 2 minus x's cancel and you get 3 times b times 3 minus 2x. Then we choose x values to make our formulae easy to solve. So if we make x equal 2, 2 is equal to, 2 minus 2 is 0, so the first term cancels. That makes 2 a good choice because we eliminate one of the constants. Sticking the 2 into the second term, 3 minus 2 times 2, 3 minus 4 is minus 1, so 2 equals minus b which gives us that b is equal to minus 2. The other x value that's convenient is the one that would make the second bracket equal to 0. That would be 3 over 2. So 3 over 2 equals, second term cancels, the one with the b in cancels, that was the point of choosing 3 over 2. The first term, 2 minus 3 over 2 is a half, so we get 3 over 2 equals a half a. Times both sides by 2, a is equal to 3. So our binomial is 3 over 3 minus 2x minus 2 over 2 minus x. And that's part A. Now to expand using binomial series, we need to do a slight rearrangement of that partial fraction. So we bring the denominators up as negative powers, so it's 3 times 3 minus 2x to the minus 1 minus 2 times 2 minus x to the minus 1. So what we need to do is to expand these two terms separately and then subtract them. So for the first one, 3 times 3 minus 2x to the minus 1 equals 3 times 3 to the minus 1, 1 minus 2/3 x to the minus 1. Now 3 times 3 to the minus 1 actually gives us 1. So we get 1 minus 2/3 to the minus 1. Expanding using the binomial series, 1 plus nx, so we get 1 plus n is minus 1. The x is minus 2/3 x. Oop, missed the x there. Plus n times n minus 1. So minus 1 times minus 2 over 2 factorial times minus 2/3 x all squared. And in this case we're going up to x cubed, so we'll need another term. So plus minus 1 times minus 2 times 1 less again, minus 3 over 3 factorial minus 2/3 x cubed, technically plus dot dot dot. Calculating, you get 1 plus 2/3 x plus 4 over 9 x squared. Remember here not that we have to square the minus 2/3, which gives us 4/9. The terms in front of the bracket actually cancel down to 1. And then the next term, the x cubed term, using our calculator, minus 1 times minus 2 times minus 3 all over 3 factorial times minus 2/3 all cubed will give us 8 over 27 x cubed. Then we need to do that with the other term. So 2 times 2 minus x to the minus 1 equals 2 times 2 to the minus 1, 1 minus a half x to the minus 1. And again, quite nicely, the 2 and the times 2 to the minus 1 is 1. Though of course this doesn't always happen in these sort of examples. They nicely cancel out to 1, and we're just left with 1 minus a half x to the minus 1. Expanding using the formula. So 1 plus nx, our n is minus 1. our x is minus half x, plus n times n minus 1, so minus 1 times minus 2. Coefficients in front of the brackets will be the same as the last example, or last part. The difference is our x is different, so what we square and cube is different. So plus minus 1 times minus 2 times minus 3. So 3 factorial. Minus half x cubed plus dot dot dot. So calculating, we're going to get 1 plus a half x plus a quarter x squared plus an 8th x cubed plus dot dot dot. And the idea is we're taking the first one and we're subtracting the second. So for the final answer, we're doing 1 take away 1, which is just 0. Then we're doing 2/3 x take away a half x, which gives us a 6. Use a calculator, of course. Then we're doing 4/9 x squared take away a quarter x squared. Which gives us 7/36. And finally we're doing 8/27 minus an 8th. We get 37/216. And that is the result of the expansion. Now of course in other cases we might have to add the term, so don't just assume it works exactly the same way each time. Now part C asked us to state the values of x for which the series is valid. Now we did 2 expansions, one of them 1 minus 2/3 x to the minus 1, so the modulus of 2/3 x has to be less than 1, which gives us that the modulus of x is less than 3/2. We had to do the other expansion as well, the 1 minus a half x to the minus 1. So a half x has to be less than 1. Implies that x is less than 2. So both these conditions have to be true at the same time. So both those at the same time, that's only the case when the modulus of x is less than 3/2. So the series is valid only when modulus x is less than 3/2, because both series are valid for that. Whereas, for example, if we went slightly above 3/2, say 1.8, it would be valid for the second expansion, but not the first. The whole point of this, binomial series can be used to find good approximations of calculations, and are one of a variety of techniques scientific calculators use to do calculations.